Hi, I'm Rory McLaren. I'm the director of the Fluid Power Academy, and I'd like to talk to you a little bit today about cavitation, this phenomenon that is somewhat confusing to many. What is the problem? Is it air? Is it starvation or air contamination of the oil? First, before I go on, I'd like to thank Fluid Power Training Institute for giving us these fabulous trainers, these training simulators to help us understand this phenomenon. And I'd also like to thank Hydrocheck for loaning us the test equipment. Hydrocheck is a company that specializes in diagnostic equipment for diagnosing and maintaining hydraulic systems. That we are going to be using two of the Fluid Power Training Institute's flagship trainers. The first and foremost, we're going to be using the Cavitation, which is the model MF200 CAV. This cavitation trainer is absolutely amazing for teaching cavitation because it is so capable of helping us understand every aspect of not only the normal operation of a hydraulic system, but also cavitation and pseudocavitation. So just a few things about the trainer itself. We've got a transparent hydraulic reservoir with a baffle which divides both the intake and the discharge. We have transparent intake and pressure lines. So the larger of the larger diameter transmission line is the intake, the smaller is the discharge. We have a gear pump, a 1.8 GPM gear pump. We have a flow meter. We have ambient and oil temperature gauges. And we also have a large vacuum gauge and also a large pressure gauge. In order to facilitate cavitation and pseudocavitation, or air contamination of the oil, we have a valve on the left-hand side of the trainer that will allow us to add or allow air to go into the intake of the pump. We have a valve here which will restrict the flow into the pump. So that can simulate a plugged screen, an overspeed condition on a pump, and so on. And then we have a valve here that we can generate resistance when we want to exacerbate the noise of cavitation. So we'll be using this trainer for demonstrating both cavitation and pseudocavitation. The other trainer we're going to be using is Fluid Power Training Institute's flagship trainer and arguably the most advanced hydraulic training simulator in the world. This particular unit has two touch screens. It is designed for teaching 40 hours plus basic or fundamental hydraulics through any level of hydraulics you want to teach, and also has the most amazing capability to teach diagnostics because every hydraulic component on the MF102 can fault in real time, and all the faults are typically wear related. So it's fabulous for teaching hydraulics troubleshooting. So we'll be using this to obviously talk about cavitation and to also get to learn a hydraulic pump's point of reference. Let's get the most important aspect of fluid power underway, and that is safety. This webinar is aimed at showing the cause and effect of cavitation and how to prevent it. Safely, it is not intended for people who have not attended a reputable course of study in basic hydraulics. Do not perform these tests or procedures if you do not have basic training. Performing these tests without the proper training can lead to severe injury, death, or substantial property damage. The author accepts no responsibility for people who suffer injury or death as a result of ignoring this warning. Almost every component performance test presented in these webinars is invasive. That is, connectors have to be loosened and removed to install diagnostic instruments. Before working on a hydraulic system, take the following life and limb saving precautions. Always lock out and tag out the energy source and jog the power to confirm that the energy source has been isolated. In other words, follow your company's protocol with respect to lockout and tagout. Next, de-energize and verify. If the hydraulic system cannot be de-energized, read the manufacturer's warnings about releasing stored hydraulic energy to the atmosphere, and then call the manufacturer and inquire as to why there is a conflict with the warning and the ability to safely de-energize the hydraulic system. Never ever remove a connector, loosen a connector, or remove a component without verifying that there is no stored energy within that leg or branch of the system. Next, each time you install or remove a transmission line, repeat the lockout procedure. And always use the symptom, observe and listen to the operator. In this webinar series that we're going to be doing with the Fluid Power Academy, we're going to call it Get to Know the Patient, because it's all about getting to know your hydraulic system in much the same way a physician knows the patient. This particular webinar is about how to prevent your hydraulic pump from dying due to cavitation. Cavitation is the cause of so many pump failures, and this is obviously a proactive webinar that helps us understand how we can prevent hydraulic pump failure from due to cavitation, either pseudo or otherwise. Here's the outline of what we're going to be discussing in the next little while. First of all, let's review the operation at the inlet side of a hydraulic pump. Let's look at what diagnostic instruments are needed to analyze the inlet side of a hydraulic pump. Let's learn how to determine a hydraulic pump's point of reference. Let's look at common symptoms associated with cavitation and pseudocavitation. We'll also look at common causes of high inlet restriction and also common causes of low inlet restriction. And then, of course, we'll do a cavitation simulator demonstration to actually see cavitation occur. First of all, to understand how oil gets into a hydraulic pump, here's a very, very simple introduction. I have an air compressor here, and I'm going to compress a reservoir that is filled with water. There's a tube that extends from the water out through the top of the reservoir, and as you can see, the compressed air is pushing the liquid out through the tube and it's spilling onto the top of the reservoir. The key word here is that the compressed air is pushing the liquid up through the tube and out of the reservoir. If we had to study how a hydraulic pump functions, it functions in exactly the same way. For example, there's an ocean of air that surrounds the earth. That ocean of air has weight. So let's weigh it. We'll take that ocean of air, we'll take 1 square inch, we measure it, it weighs 14.7 pounds per square inch. That pressure through the breather on top of the reservoir pushes down on the oil, and as the pump rotates, all pumps are partial vacuum generating devices. So inside the pump, we're creating a vacuum. Obviously, since nature abhors a vacuum, the air pressure, by virtue of atmospheric pressure, pushes the oil into the pump to fill the void. And that is obviously what creates flow. This is a very, very delicate balance, because the only thing pushing oil into a hydraulic pump is the pressure by virtue of atmospheric pressure at whatever altitude this pump is operating at. All pumps work on the same basis by virtue of increasing and decreasing volume. Here's a very simple single piston pump that will help us understand that. For example, I have a vacuum gauge here. If I pull the lever, I'll create a partial void or vacuum behind the piston. Atmospheric pressure will push the oil into the chamber. I'll put a pressure gauge in now and I'll push the lever in the opposite direction. Check valve closes, check valve opens, and of course the pushing action of the piston pushes the oil out of the pump. And that's simply how all hydraulic pumps work, on the basis of an increasing and decreasing volume. Here again is a hydraulic pump. Let's start it up. And again, what's going to happen is as the gears unmesh, they'll form a vacuum. Atmospheric pressure pushing on top of the oil will push the oil into the gear. So there you can see that the pump is creating a vacuum. Atmospheric pressure pushing on top of the oil is pushing the oil into the pump, thereby creating flow. If we draw a line through the center of every single hydraulic pump, one side of the pump operates in a vacuum while the opposite side of the pump operates against resistance, or which becomes pressure, whatever the pressure needs of the system are. All right, so let's move on. Maximum inlet restriction for the various types of pumps are as follows. There are three popular pumps in the industry. We've got piston pumps, vane pumps, and gear pumps. The respective volumetric efficiencies per engineering specifications provided by the pump manufacturers are: piston pumps, maximum inlet restriction 4 inches of mercury at approximately 135 degrees Fahrenheit. Vane pumps, 6 inches of mercury at, again, 135 degrees Fahrenheit. And gear pumps have the highest tolerance for inlet restriction, 8 inches of mercury at normal operating temperature. These numbers, just so that we understand each other, these numbers are provided by the pump manufacturer. When the pump manufacturer sells the pump to a user, an end user, it is the end user's responsibility to see that the hydraulic pump is in conformance with the maximum inlet restrictions provided by the pump manufacturer. This is an important note, and we'll talk a little bit more about that as we move forward. In order to check inlet restriction on any hydraulic pump, we need the following diagnostic instruments. We need a temperature gauge, since temperature is vital. We need a vacuum gauge, 0 to 30 inches of mercury. We need a tachometer, and of course, we also need to know what the flow rate is. Make sure the flow is correct. Here's an isometric view of a hydraulic system with the various diagnostic equipment in place. Again, we're checking both inlet and the oil temperature, and of course ambient temperature. We're looking at the speed at which the pump rotates. We're looking at inlet restriction at the inlet side of the pump, and the vacuum gauge needs to be installed as close to the inlet of the pump as possible. In this case, we also have a pressure gauge and a flow meter. I conducted a 10-year study of hydraulic pump failures, and I found a very disturbing trend. While pump inlet restriction was monitored on less than 1% of those pumps, cavitation was evident in 75% of those pumps that I disassembled. In other words, in a period of 10 years, 75% of open loop pumps had either failed due to cavitation, or there were signs that the pump had suffered this condition. And that's alarming. It's only disturbing because over 99% of pumps are not, the inlet restriction on these pumps is not monitored on a routine maintenance basis. So here's my point. I'm taking, for example, here, technical specifications from Danfoss, Sauer Danfoss, just as an example. As we can see, Danfoss, the maximum inlet restriction on this particular Danfoss pump is 6 inches of mercury at normal operating temperature. 6 inches of mercury at normal operating temperature. Now, this information is for the consumption of the hydraulic system design engineer. In other words, if an end user, a manufacturer, purchases a Danfoss pump, Danfoss's engineers recommend that when the company puts that hydraulic pump into service in their piece of equipment, that the design engineer's responsibility is to make sure that the pump is conforms to the specification. Here's the problem. What has happened is that the manufacturers, the design engineers, have evidently passed this information through into the service manuals for various pieces of equipment. And that's problematic. In other words, the information that is for the purpose of engineering has been shifted or transferred through to maintenance. Again, over the years, I've called a number of manufacturers and asked specifically, what is the inlet restriction on a given pump in a given application? And oftentimes, or more often than not, the engineers will say to me, well, the information you're looking for is in the service manual. Well, actually, it's not. The information I'm looking for is the information that the design engineer should have used in order to determine that they were in conformance with the manufacturer of the pump's specifications. In other words, again, the information in the service manual is generally the information that the design engineers should have used on starting up and prototype on the piece of equipment. Let me show you what I mean by this. One of the most important things we can do with a hydraulic system is get to know it. Get to know the patient. It is imperative to determine every hydraulic pumps, just as one example, inlet restriction point of reference. In other words, if the manufacturer of the pump says, for example, on a gear pump that the maximum inlet restriction is 8 inches of mercury, then the designer needs to make sure that in the design of the system that we do not exceed the 8 inches of mercury at normal operating temperature, but the information that we need for ongoing proactive maintenance is not the information provided by the manufacturer for the purpose of engineering, but it's the point of reference that was established by the end user, by the manufacturer of the machine. In other words, if a pump's normal inlet restriction is unknown, it is going to be difficult, impossible to determine or detect abnormal variations in performance. Let me give an example. We have on the MF102 here an axial piston pump. 1 gallon per minute axial piston pump. I have installed at the inlet of the pump a vacuum gauge. So it's designed, this is designed so that we can non-invasively introduce a vacuum gauge, which should be true of every hydraulic pump. Every hydraulic vacuum inlet restriction is so critical because so many things related to service can change inlet restriction. Some things as simple as screens in reservoirs, a breather on top of a reservoir, a speed, an RPM change if it's a variable speed drive, an overspeed condition. Well, if something outside or some normal situation like a breather plugging or a screen plugging can affect a pump's inlet restriction, then surely we must monitor that on a proactive maintenance basis. What I'm going to do is I'm going to start it up and I'm going to determine what the point of reference is for this pump's inlet restriction. Bear in mind that this is an axial piston pump, and according to rule of thumb, the maximum inlet restriction is 4 inches of mercury. So I'm going to remove the lock from the machine because it's been safely locked out. I'll remove the lock from the machine, and then I'll turn it on. The inlet restriction at 1 gallon per minute is 3 inches of mercury. For as long as this pump is operating at this altitude and at this temperature, the inlet restriction that we have just learned here can never change. Never change. In other words, let me just go back on that. This is an axial piston pump. According to rule of thumb, the maximum inlet restriction is 135 degrees. The maximum inlet restriction is 4 inches of mercury at 135 degrees Fahrenheit. What we did was we started the pump operating at rated flow, temperature of the oil right now at about 68 degrees Fahrenheit, so it's only going to get better as it heats up, but the inlet restriction point of reference is 3 inches of mercury. So that's what we've established. In other words, from a design point of view, I have established that I am within the 4 inches of mercury recommended by the pump manufacturer. For the consumption of people that maintain the hydraulic system, I've got to make sure that at this altitude, about 4,600 feet above sea level, and at this temperature, which again is about 68 degrees Fahrenheit, the inlet restriction point of reference for this pump is 3 inches of mercury. And that is a vital operating parameter which needs to be monitored on a routine maintenance basis. Let me explain. So for example, we tested an axial piston pump. The manufacturer's specification, maximum 4 inches of mercury at 135 degrees Fahrenheit. What did we determine? We determined that the point of reference is 3 inches of mercury. And that's set in stone. For the rest of this pump's life in this application, again, at this temperature and this altitude and this flow rate, that number should never ever change, unless, of course, there's a problem. A problem at a pump's inlet, the inlet side of a pump, can cause inlet restriction to do one of two things. It can either go up or it can go down. Up or down. In other words, if this is my point of reference, which again we've established in this case, 3 inches of mercury, anything above 3 is undesirable and anything below 3 is undesirable. This refutes the whole concept that the lower a pump's inlet restriction, the better. I think if you had to read books about pump inlet restriction, that's a general statement. And technically that's correct. The lower the inlet restriction on a pump, the better. That's true. Except for one problem. I must have a point of reference. Use of this reasoning, if a pump in our example has a point of reference of 3 inches of mercury, then any decrease in inlet restriction would be acceptable, which, as we've just said, is erroneous. If a normal operating parameter is unknown, it makes detecting an abnormal variation in that parameter difficult or impossible to determine. Now, let's move over to the cavitation simulator. Before I demonstrate cavitation and pseudocavitation, let me take a moment to introduce you to this fabulous trainer. First of all, it has a completely transparent hydraulic reservoir built to correct design specifications. It's baffled, which separates the return and the intake to the pump, which is, of course, prudent design. Next, we have a completely transparent intake to my pump, the large diameter tube, and the smaller diameter tube is the pressure line coming out the other side of the pump. Both, as you can see, are transparent. I have a 1.8 gallon per minute gear pump, and bear in mind our rule of thumb for inlet restriction on a gear pump is 8 inches of mercury at 135 degrees Fahrenheit, at normal operating temperature. I also have a flow meter, an analog 0 to 2 GPM flow meter. I have a 4-inch 0 to 30 inches of mercury vacuum gauge, and I have a 4-inch pressure gauge. I also have a gauge which shows me both ambient and oil temperature. Along the bottom here we have a valve here that will allow me to let air go into the intake of the pump. Next, I have a valve that will allow me to restrict the flow going into the pump. And this handle here is for a needle valve, which will allow me to create resistance to flow so that we can understand how the pressure relates to, of course, the noise of cavitation. All right, so we're going to do a demonstration on the cavitation. We're going to begin with cavitation. So in other words, what I'm about to do is we'll start it up. We'll get to know the patient. In other words, what we'll look at is what are the normal operating parameters of that particular hydraulic system. Then what I'll do is I'll demonstrate cavitation. Cavitation by definition is the formation and collapse of gaseous cavities within a liquid. In other words, when I subject a hydraulic oil, if hydraulic oil is made up of 10% dissolved air by volume, up to and during cavitation, the dissolved air comes out of the liquid. So try to imagine you have a pop bottle with translucent liquid. When we take the top off the bottle, it will appear to be filled with gaseous cavities. It'll fizz. The only reason why it's doing that is because when we took the top off the bottle, we released the pressure. When the pressure was off the liquid, the dissolved air came out of the liquid. Hydraulic oil is exactly the same. If we subject hydraulic oil to a vacuum, we will allow the dissolved air to come out of the oil. Well, that's fine if we're looking at what's going on the inlet side of the pump. But if you take a gaseous cavity through the pump, and on the other side of the pump, it's going against a resistance of 1,000, 2,000, or 3,000 psi, there's no doubt that that gaseous cavity is going to implode. And the force of that implosion is not measured in pounds of force per square inch, it's measured in tons of force per square inch. All right. So common symptoms of cavitation in a hydraulic system are, and these are both cavitation and pseudocavitation. Just so we understand each other, pseudocavitation is air contamination of the oil. In other words, I'm not starving the pump for oil as in cavitation. What's happening is I've got an infeed of air to the intake of the pump that is coming in through a low oil level, through a cracked connector, etc. If I'm adding air, which is turning my pump into a semi-oil pump air compressor, then obviously I'm going to pump air into my system, and this is going to aerate my entire hydraulic system. This is very bad. So there's a difference. And one is visible. In other words, if I look at my sight glass on my hydraulic tank, for example, and I see foam in the sight glass, this is indicative of pseudocavitation. So cavitation has everything to do with the dissolved air in the oil and a liquid's vapor pressure. Pseudocavitation has everything to do with air going into the inlet side of the pump from an outside source. Both cavitation and pseudocavitation will yield noise. The pump will be noisy. Now, it's hard to discern from the noise whether it's cavitation or pseudocavitation. There might be a slight difference, but noise is not anything that I would use in order to determine whether I've got cavitation or pseudocavitation. Next, both will lose flow. Whether you're cavitating, meaning you've got starvation, or aeration, both, you're going to lose flow. Next, I will lose pressure, which means I'm going to lose power. Either one. If I lose flow and or pressure, I'm going to lose power. The other thing cavitation will do, if it persists, it'll start to elevate the operating temperature of the oil. And last but not least, if it's pseudocavitation, or if you will, air contamination of the oil, the oil is going to foam. We'll talk about that in just a moment. Now, what I would like to do is just go back to what we determined on the MF102. We determined that the inlet restriction point of reference is 3 inches of mercury. The manufacturer says we can be no more than 4. If I'm trending, which I should be doing, checking inlet restriction on a pump every 30 days based on an 8-hour shift, then if I'm trending, I will see that in January I have 3 inches of mercury, February 3, March 3, but let's say, for example, in April, the inlet restriction went up to 7 inches of mercury. This is definitely a red flag. My this has to be nipped in the bud. This cannot be left. Cavitation is a systemic problem. It's a systemic catastrophic condition. So I've got to nip this in the bud. So the first thing I want to do is go and determine what made the inlet restriction rise. So you see how useful it is to have a point of reference? Let's say, for argument's sake, I did not have a point of reference. Well, that's a gear pump on the simulator that I'm about to demonstrate. The maximum is inlet restriction on that pump is 8 inches of mercury by rule of thumb. 8 inches of mercury at 135 degrees Fahrenheit. Well, 7 inches is within the 8. However, what if my point of reference on the gear pump was 3 inches of mercury? Can you see that if I didn't know what my point of reference is, I would automatically assume that there was nothing wrong at the inlet side of the pump. And that's why it's critical to determine every pump's inlet restriction point of reference. So let me demonstrate high inlet restriction. All right, so what I'm going to do is let's start it up. Open this valve here. All valves shut off. I'll start it up. And let's look at what the normal operating parameters of this hydraulic system are. What are they? Well, first of all, if I start here, I've got 1.8 gallons per minute. That's my pump's flow rate. Next, my inlet restriction is 4 inches of mercury, 4. Pressure is nominal or low right now. My ambient temperature is 75 degrees Fahrenheit, and my oil temperature is also 75 degrees Fahrenheit. As you can see here, there is absolutely no turbulence in the intake. We've got what we call a laminar flow. I have no turbulence whatsoever in the discharge line, and there is no evidence that oil is even flowing in the reservoir. No evidence whatsoever. This is a perfect situation for a hydraulic system. Now, what I'm going to do is, again, let me just remind you, this is a 1.8 gallon per minute gear pump. Maximum inlet restriction by point of reference, or at least by the manufacturer's specification, is 8 inches of mercury at normal operating temperature. I have 5 inches of mercury, which is this particular hydraulic system's point of reference. So for the rest of time, as long as this hydraulic system is operating at 1.8 GPM, at 75 degrees ambient and 75 degrees oil temperature, at this altitude, that number should never change. Any increase or decrease in that 5 inches of mercury would be indicative of a problem in the system, since my point of reference is 5 inches of mercury. Now what I'm going to do, I'm going to create some resistance. So I'm going to close this valve slowly and push the resistance in the system up to 700 pounds per square inch. So the pump is pumping against a resistance right now of 700 psi. So once again, my operating parameters are 1.8 GPM, 700 psi. Now I'm going to slowly resist flow going into the pump, which is going to simulate either a plug screen or an overspeed condition. So I'm going to resist the flow, and you'll see the inlet restriction gradually rise. We'll get to a point where you will see the dissolved air coming out of the oil in the inlet side of the pump. In other words, in a nutshell, or in a sense, I'm going to take the pressure off the oil. The dissolved air is going to obviously come out of the oil. So here we go. As I increase resistance, on the inlet side of the pump here, I can see the dissolved air has come out of the oil. Looking back at my parameters, I have lost flow. My flow's dropped down to 1.2 GPM. My pressure was 700 PSI. My pressure is now down at about 350 PSI, which means I'm obviously going to lose power. There is absolutely no evidence of cavitation in either the pressure line or in the reservoir. There is no evidence of it. In other words, as some people refer to cavitation, if they see foam in the oil, they'll say the pump is cavitating. Well, actually it's not. Because as you can see, the pump is cavitating and there is no evidence of cavitation in the reservoir. So once again, let me back up. What we have is we have a 1.8 GPM gear pump. My maximum inlet restriction, by rule of thumb, is 8 inches of mercury. My pressure is, I set the pressure at 700 PSI, and then I restricted the flow going into the pump up to about 12 inches of mercury. What happened was, as the oil was subjected to a vacuum, or let's say a higher than normal vacuum, the dissolved air came out of the oil, it went through the pump, and the gaseous cavity imploded. The oil or the air then went back into suspension, so you can no longer see it in the oil. That is cavitation. The formation and collapse within the pump of the gaseous cavity within the liquid. Now, that's what happens when I go high. In other words, we said we need to know what the point of reference is, such that if the inlet restriction starts to go up or starts to go down, we can nip it in the bud. We can take urgent action in order to mitigate the problem. So let's go to the flip side of the coin. First of all, the following are the general, this is a list of the most common reasons why we would have cavitation. First of all, low ambient temperature, pump overspeed condition, oil viscosity, the incorrect oil, the oil's too cold. Suction screen, maybe partially plugged or undersized. Suction filter, also the same problem. Suction line diameter, that's an inherent design problem, for example. It's not the right diameter, it's too long, or it's the wrong type. Next, the reservoir of pump and reservoir, the relationship of the reservoir to the pump, and that is, by rule of thumb, a pump should never be mounted more than 3 feet above an oil level. So that could be a problem. Next is the isolator valve. Some designers will put an isolator valve between a pump and a reservoir for the purpose of shutting the pump flow off in the event that we need to remove a pump for service or whatever the case may be. That's not always a good idea. And sometimes, unfortunately, when we size the shut-off valve, for example, for 1.25 inches, it will not be it might be 1.25 inches by virtue of the thread, but going through the center of the valve might drop down to 1 inch, which creates, of course, a restriction in the flow path. And that's fine, except in most cases, the person that designed the system never goes to check to see what the inlet restriction point of reference is, or even if the inlet restriction is in compliance with the pump manufacturer's specifications. Next, we have a vacuum in the hydraulic reservoir. That could be because of a breather that is plugged on a reservoir because a pressurized reservoir filler cap has malfunctioned. The pump inlet port, the diameter is incorrect. And of course, the reservoir is not pressurized because some manufacturers require the reservoir to be pressurized. And if it's not pressurized, it's going to cause problems at the inlet of the pump. All right, so let's go back to now the pseudocavitation. Let's study this phenomenon. So what we're going to do now is, if I'm now trending the inlet restriction of my pump, again using 3 inches of mercury as an example, we can see that in January I'm normal, in February the pump is at normal, in March the pump is at normal, but in April it drops from 3 inches of mercury down to 1. This is alarming. In other words, once again, red flag. And I've got to nip this in the bud. I cannot leave it to operate. If I'm aware that a hydraulic pump is cavitating, I cannot say, well, let's just run it to the end of the shift. Any problem with the system is, the first question we have to ask ourselves is, this is a pending catastrophic failure. It can certainly result in that. And it's going to be systemic. So my first question is always, if I am aware that there's a problem, but I want to get to the end of the shift, if during that period of time the unit fails, could the operator lose control of the machine? Could it cause an accident? So if it's just production and I'm going to blow pump parts away, that's fine. That's fine. If we have the money to mitigate that, no problem. However, before I worry about that, I have to worry about, will it render the machine unsafe? And that's why when we see abnormalities in the performance of hydraulic components, we need to address them immediately. No waiting. All right, so now what I'm going to do is we're going to look at now what happens when the inlet restriction goes down. So let's go back to the cavitation trainer and demonstrate this phenomenon, which is now called pseudocavitation. So what we're going to do now is we'll start it back up again. Once again, I've confirmed that my pump flow is 1.8 gallons per minute. My inlet restriction is about 5 inches of mercury. My pressure is 700 pounds per square inch. And again, we can see that there is no evidence of cavitation. So my point of reference I'm at, and now what we're going to do is we're going to go down, meaning we're going to simulate a condition whereby my inlet restriction inexplicably, instead of being 3 inches of mercury, drop down to, let's say, 1. All right, so I'm going to open this valve here, which is going to let air go into the inlet side of my pump. So we will see air begin to flow in from the outside. I've immediately dropped my inlet restriction. So I've gone from a normal of 5 inches of mercury down to 1. This is a systemic catastrophic condition because now you can see that I am taking air into the intake, it's pumping the air through the pump, and it's now aerating the oil in the reservoir. So you can see I'm forming a cloud of air across the top of the oil. Bear in mind that whatever you see in here represents what the oil will look like throughout the hydraulic system. That's why we call this a systemic catastrophic condition. So let me back up. Cavitation is a systemic problem because when the implosion occurs, it pulls little pieces of the pump out and feeds them downline into the system. Every piece of contamination we feed into a hydraulic system is an abrasive seed, and its growth is exponential. Today it's 1, tomorrow it's 10, the next day it's 50, and so on and so forth. However, it doesn't affect the purpose of the oil in its entirety, meaning hydraulic oil is for purposes. I transmit power with it, I seal with it, I lubricate with it, and I carry heat away with it. So when the pump is cavitating, The only damage, and I'm not undermining how serious that is, but it doesn't affect the purpose of the oil throughout the system. However, as you can see here, PseudoCavitation or aeration has aerated the oil. In other words, what you're seeing in this reservoir is representative of the oil throughout the hydraulic system. So once again, I cannot transmit power with foam. I cannot seal clearances with foam. I cannot lubricate with foam. I cannot carry heat away with foam. This is a systemic catastrophic condition that needs to be nipped in the bud to prevent widespread failure. So, once again, let me start it up. My pump flow, as we learned, was 1.8 GPM, and now that I'm allowing air to go into my pump, my flow is compromised. So, my flow is erratic, and I'm going from about 1.7 GPM down to about 1.2. My pressure is erratic. It's going or fluctuating between 650 psi and 100 psi. I can see a gain in the oil temperature. This condition is called PseudoCavitation, or if you will, air contamination of the oil. Sometimes when people look in a sight glass and they see that the oil has changed its complexion like it has here, we'll get confused between aeration and water contamination of the oil, because water will change the complexion of the oil as well. So this is a catastrophic, systemic condition that needs to be nipped in the bud. So what we've demonstrated, let's just summarize, is number one, we determined the pumps. First of all, we determined that the manufacturer of the pump gives us a number that the manufacturer of the machine, the hydraulic system designer, must not exceed. Once the machine has been built with that particular pump, then it's the engineer's responsibility to go to the shop floor on prototype and first of all determine if the system is designed within the manufacturer's recommendations. And then once we've established that we are within those guidelines, then the next thing we need to do is publish for the consumption of maintenance people what that pump's point of reference is. In this particular instance, we said we've got an axial piston pump. The manufacturer's maximum recommendation is 4 inches of mercury at 135 degrees Fahrenheit. We established with a vacuum gauge that the point of reference is 3 inches of mercury, and then we went about our business doing two things. One, we first of all demonstrated what happens if inlet restriction goes up, and we demonstrated cavitation, which was the formation and collapse of gaseous cavities within the liquid. That was the first demonstration. Then what we did was we let air go into the inlet of the pump, and we let the inlet restriction went down, and we proved, of course, that lower isn't better when you have a point of reference. So those are the things we've demonstrated insofar as what is happening inside a hydraulic system. Causes of PseudoCavitation are a number. Number one is a low oil level. If we neglect oil levels, of course, we're going to let air go into intake of our pumps. Next is reservoir baffle design. If the machine is moving and you're momentarily taking in air, it's going to cause cavitation or PseudoCavitation. Incline operation, again, we have to be very careful that we don't exceed the manufacturer's recommendations for incline operation. Next is turbulence in the reservoir, created by high return flows due to the volume differences in cylinders, discharging oil from accumulators. Pump suction lines, we got loose or cracked connectors, cracked welds, loosened clamps, etc. Accumulators, of course, that's a one-shot where you've lost an accumulator bladder and you've now started pumping nitrogen, well, of course you won't know, but that into a hydraulic system. The next could be the pump reservoir isolator valve. It's got a a seal, a gland seal that is leaking, so air is going in through the isolator valve. And of course, on internally drained pumps, you could have air going in through the pump shaft seal. Now, I'm going to go back to the cavitation trainer for a moment, and I'm going to demonstrate another problem, and that is what happens when we drop oil in on top of oil. So this is another problem. In other words, if I see foam in the sight glass, it could very well be because I'm dropping oil in on top of oil. So this would typically be where I've neglected the oil level, or it could be because a designer trying to keep a case pressure down in a pump or motor is discharging oil above the oil level. So no oil that is flowing, or return line that is flowing oil, should ever discharge above the oil level in a hydraulic reservoir. For this demonstration, I'm going to open a valve at the back of the simulator, which is going to start to drain the oil out of the reservoir. So the white tube inside the reservoir is the return line. So now what I'm doing is I'm going to let it gradually lower, because I've opened the valve and I'm draining the oil out, and in a moment the return line will be above the oil level. So I'll start it up. So I've closed off the valve that lets the air go in. I'm going to start it up. Now, as you can see, the oil level is dropping and the discharge flow is no longer below the oil level, it's above the oil level. So once again, you can see the immense amount of turbulence that is being generated by dropping the oil in on top of the oil. This is a very, very undesirable situation, and this comes from, again, from discharging any return line above the oil level. All return lines should terminate at least, by rule of thumb, 14 to 16 inches below the oil level. A very undesirable situation. The other thing this simulator is going to demonstrate is, if you look at the return here, you can actually physically see vortex occurring. So as I've gone down in stages now, I can literally see a vortex where I'm vortexing oil into the intake of the pump. Now, in other words, I guess the point is you don't have to expose the intake in order to vortex air into the intake. So if I've designed a hydraulic system whereby I haven't taken into consideration the volume displaced by large bore hydraulic cylinders, number one. Number two, the volume occupied by hydraulic or hydropneumatic accumulators, I could, by virtue of design or oversight, have a problem with cavitation, because when I extend cylinder rods, or I've charged, I've stored energy in my accumulators, my oil levels have dropped to a point where we're encroaching on the intake, and we are now vortexing air into the intake of the pump. That's another consideration in terms of design. So as we can see here, we can demonstrate all of cavitation, pseudo-cavitation, vortex, etc. The nice thing about the MF200 cavitation simulator is it leaves nothing, as you can see, it leaves nothing to the imagination, because we can actually physically see cavitation occurring. All right, so let's get back to the slides now, and we'll talk a little bit more about pseudo-cavitation. As we've demonstrated, it can also be caused by poor hydraulic reservoir design and poor maintenance. Again, back to what we've just mentioned about this, the reservoir was not sized correctly to accommodate the volume that is taken up by cylinders, large bore cylinders, and of course accumulators, and of course poor maintenance procedures, meaning that I'm not maintaining my oil levels. So here are the important facts about testing the inlet or vacuum side of any hydraulic pump. A, pump inlet restriction is the amount of vacuum generated or measured in inches of mercury which is generated at the inlet or vacuum side of a pump while the pump is operating at rated flow. So be careful of pumps that are variable volume, pressure compensated load sensing. They have to be on full stroke, full flow in order to check inlet restriction. B, unless otherwise specified, pump inlet restriction is given as a maximum value at a predetermined temperature. Typically normal operating temperature. For example, if the maximum inlet restriction is 8 inches of mercury, the pump's inlet restriction can be any amount less than 8 inches of mercury, but no more than 8. C, to measure pump inlet restriction, a vacuum gauge must be installed at the pump's inlet port, as close to the inlet port as possible. Bear in mind that unlike a pressure gauge, which reads from the point it is installed in the circuit to the end of the line, a vacuum gauge reads from the point it is installed in the circuit to the beginning of the line. D, it is vital to establish a pump's inlet restriction point of reference when a pump is put into service. Without a point of reference, it is difficult to determine if a pump's inlet restriction is normal or abnormal. So bear in mind that over 99% of hydraulic pumps operating in service today have no means for maintenance people to non-invasively check inlet restriction. It's not possible. Number one. Number two, manufacturers of hydraulic system designers have inadvertently, it seems, given the information that is for their consumption, meaning the manufacturer of the pump's maximum inlet restrictions, and they've passed it through to maintenance. That's not the information maintenance people need. The information provided by the pump manufacturers for the consumption of the design engineer. The design engineer's responsibility is to, once the machine is on the floor, starting up, prototyped, the engineer's responsibility is to go to check to see that the design lies within those parameters that, determined by the pump manufacturer. Once the engineer has determined that we're within those parameters, then the engineer's next step is to work in concert with the people that produce the service manuals and give the people that produce the service manuals the point of reference for what that inlet restriction is at temperature and altitude. That's the number maintenance people need to have. The problem with designing with hydraulic pumps is that no two identical pumps have the same inlet restriction in different applications. For example, engineer A may mount the pump above the oil level, and engineer may mount the same pump below the oil level. Engineer A may put a suction screen in the tank, and engineer B may not. Engineer A may have a 90-degree bend going into the pump, and engineer B may not. That's why every single hydraulic pump in every application has a unique set of operating parameters with respect to inlet restriction. When the vacuum generated at the inlet side of a pump is higher or lower than normal, it will generally cause a condition called cavitation. Be careful how you interpret pump inlet restriction. For example, if a pump's maximum inlet restriction is 8 inches of mercury at normal operating temperature, it means that the inlet restriction can be less than 8 inches of mercury, but no more than 8. In other words, the lower the better. However, this logic is only valid if there's a point of reference. Example, if a pump's maximum inlet restriction is 8 inches of mercury at 135 degrees Fahrenheit, and the point of reference is 4 inches at 135 degrees Fahrenheit, if the inlet restriction drops to 2 inches of mercury, as we've just witnessed on the cavitation simulator, there is a serious problem. In this case, lower is definitely not better. G, cavitation by definition is the formation and collapse of gaseous cavities in a liquid. Again, we demonstrated that. When we created a higher than normal inlet condition, we literally saw the dissolved air coming out of the oil, and we saw that once the implosion occurred in the pump, that it went back into suspension. In other words, the gaseous cavity disappeared. When the inlet or vacuum side of a pump is restricted, inlet restriction will be higher than normal, which is again cavitation. And again, when air enters the inlet side of the of a pump inlet restriction will be lower than normal, which is typically referred to as pseudocavitation. Again, the leading causes of pump failure are contamination, the single leading cause of pump failure, contamination, shaft misalignment, high pressure, excessive oil temperature, and excessive speed. When checking inlet restriction on a variable volume pump, example, pressure compensating or load sensing, it is important to make sure the pump is operating at maximum rated flow during the test. I encourage engineers to make it possible for maintenance people to do inlet restriction testing. In other words, make it possible for, in the design of the machine, to bring a pump onto full stroke without having to radio to an operator or try to get involved the operator on how to move an actuator that would facilitate flow. Most of the time you can't get the pump fully unloaded anyway, because in designing with pressure compensated load sensing pumps, we never design to utilize 100% of the flow at any given time. So it's very difficult to check inlet restriction or even set the pump's flow if it's got flow adjusting screws unless I can completely unload the pump. Pump flow is proportional to the speed at which it rotates. Excessive flow caused by pump overspeeding could adversely affect inlet restriction. Therefore, pump speed must be checked when diagnosing for high inlet restriction. This is particularly true of variable speed drive applications. Proactive maintenance. A pump's inlet restriction must be checked every 30 days based on an 8-hour shift. Factors that can negatively influence a pump's inlet restriction are ambient temperature, pump speed, elevation, oil viscosity, and of course, reservoir breathers, screens in the reservoir, etc. So, that wraps up this webinar on inlet restriction. I certainly hope it's been helpful to you. If anybody wants any further information, you'll see them on at the end of this, you'll find a slide that's got information about the simulators I used for the presentation, and also about HydroCheck, who was kind enough to loan us the diagnostic equipment for this presentation. Please look to the Fluid Power Academy for more webinars. We're going to be doing a lot of in-field work, showing people how to safely and effectively test hydraulic components. So until then, be safe. Take care.